right? And so to review, we talked about classifiers last time. Now, classifiers are different from regressives. The fundamental difference is in classifiers, the output variable is identifying a class within a category. For example, we are telling whether an animal, given its characteristics as input, is a cow or a duck or a horse and so forth. That is an identification. So that brought up the concept of a category of classes, a finite set of things, and you have to pick one. There is also multi-select classifiers, but we won't go into that now. For all practical purposes, let's consider one. So a thing is, if you give the height, the weight, the size, the presence of horns or not, and so on and so forth, hooves and so forth, you have to tell, the machine has to tell whether something is a cow or a duck. To be able to do so is saying that you are doing classification. Implicit in classification is you're doing mostly correct classification. An algorithm that is able to do that is called a classifier. So as I review this material, guys, if you have questions, do please raise your hand and speak up. Now, we took the example of cows and ducks, and we looked at how we took just two features, weight and size of a cow or a duck. And we looked into the feature space where x-axis is the size, y-axis is the weight. So this is called the feature space. The word is feature space, the input space or the feature space. So in the feature space looks like this picture on the left-hand side. You know that the ducts are light and small, so they occupy the lower, closer to the origin region. And they, all the ducts, their weights or their data points, they cluster around and they look like a bell curve in one dimension and a bell hill in multiple dimensions. Right? It's just a rounded hill kind of thing. When you have this, and likewise for cows, the hill is much more broad. Cows has a cows have a much longer variance, bigger variance in weight. But nonetheless, if we were to sort of squint and not look at that too carefully, we can say that they look somewhat identical bell hills. Right? If you do that, then creating a decision boundary is quite easy. You connect the two hilltops, which I've done here with the green line, and then you take sort of the perpendicular bisector of those, and that becomes a good decision boundary. So that brings up the decision boundary. Decision boundary partitions the feature space into regions, one region for one class, right? So the lower region on the lower side of the decision boundary, any data point that will be found will have to be called a duck. Any data point found on the upper right-hand side of the decision boundary will be called a cow. So that makes for a classifier. This particular classifier, this way of doing it, is called linear discriminant analysis. It discriminates based on one fundamental assumption, which may or may not be true with data. It makes an assumption that the classes are well separated in the feature space. That's an important point, guys. Remember, this algorithm will work only when data is well separated in the feature space. If it is not well separated, then its accuracy begins to sort of go down. And not only are they well separated, they look like bell curves. Now, what happens when they overlap? We'll talk a little bit about that today. But in general, one fundamental requirement is that all the data points of a class are clustered together in approximately a bell hill of some sort. Then this sort of algorithm works very well. Now, so these are the assumptions I talked about. Uh, the second assumption is they are more or less like bell hills. For linear discriminant analysis, the underlying assumption was that all the bell hills look similar. The shape of the variance, they share the same variance or spread, at least approximately. So it will just bell hills located at different places in the feature space. On the other hand, if the bell hills don't look alike, like for example, in cows and ducks, it's rather stretching it. If we say that the two bell hills look alike, they don't. The cow will have a much more spread out bell hill. The variance is high in weight. A cow can be 500, I suppose, or 600 pounds plus minus to 300 pounds. Whereas a duck's weight will be pretty narrow, let's say about, I don't know how much ducks weigh, let's say 10 pounds plus minus 5 pounds or something like that, right? 5, 6 pounds. So, so the variances can be different, but so when that becomes an issue, and you have to account for the fact that not only are the bell hills located at different places, but they also have different variances, then there's a generalization or the extension of linear discriminant analysis. It is called quadratic discriminant analysis. What the way quadratic discriminant analysis shows for is that the decision boundaries become curves. They become parabolic curves, or quadratic curves. Sort of, they are not straight lines anymore. That's the only distinguishing feature. Now, sometimes you can use that to your advantage, as we will do. For example, when we do the labs, you'll notice that in particular in dataset 3, you will be using quadratic discriminant analysis. Quite an advantage. Linear discriminant analysis won't work there. So that is something to know. The other point with discriminant analysis is it can not only do binary classification, a situation in which you're distinguishing between just cows and ducks, but you can actually put in as many animals as you want. Suppose you bring in a horse, now you have a triangular situation. And so you connect the hilltops of the triangle of the each of the bell hills, and you just find the bisectors, of the connecting lines, and then you will end up with this decision boundary. You'll end up segmenting or partitioning the feature space here into 3 regions. So, guys, any questions so far? I hope this looks like a recap of what we did the previous time. If you did not understand the last time, or you want me to repeat the explanation, now is the time to speak up. So this is that. So in simple terms, a classifier geometrically partitions the feature space into disjoint regions, with each region belonging to one of the classifiers. So it is a property not just of the discriminant analysis, but of all classifiers. It's a universal property. What classifiers do from a geometric perspective is they take the feature space and they create disjoint partitions or regions of the feature space and give each partition a class, one class only. Now, a review of the quad discriminant was that suppose the cows and the ducks, their variances, the hills spreads are different. Then all it does is, as this picture shows, it makes it into a curve. Are we together? That is that. So now that's a recap. With that, I would like to move on to finish off the discriminant analysis with one final consideration.
Asif, I have one question here. On the if the classes on the input feature have some overlap, so we cannot apply the classification at all.
No, we can. In fact, that's the topic I'm about to cover.
Okay.
So I'll cover it right. Any other questions, guys? So let me take this example in one dimension.
Yeah, so for Asif, so for LDA, you said like we can have like more than 2 classes where we can, as long as it's a straight line, we can.
No, not just straight line. Both for linear and quadratic, which has curves. Basically, in discriminant analysis, the only underlying assumptions are, let's go back to the assumptions. The only assumptions are that each class is clustered separately around a different point in the feature space. Right? And
Okay, got it.
those are essentially bell hills. Other than that, there are no assumptions. Are we together? Like, for example, if
Asif,
yeah,
Do you have to define a loss function here before you divide or create the discriminant?
So the question is, how in the world do you solve for that? The loss function in linear regression was some squared error. What is the loss function for classifiers? That too is the topic. Today we'll do that. Time permitting, we'll do that today. Or we'll do that tomorrow, because that's a big topic in itself. These two loss functions drive are very dominant in the machine learning world. The loss function for regression and the loss function for classification. And I will talk about that, but for that we need to build up a bit of a mathematical architecture. It turns out that the loss function for classifiers requires us to introduce one more concept called MLA, maximum likelihood estimator. And because it's a little bit of a broad topic, we may not do it today. Today, I will finish this classifier, the discriminant analysis, and then I'll also like to finish the topic of logistic regression. Those are the topics for today. Next time I'll cover it. So hold the thought in your mind till the next time. So now I'll deal with overlapping hills. Overlapping data, right? Geometrically, it means overlapping hills. So how does this situation look like? Let's take one dimension for 1D. Suppose this is, in fact, I will not bring about the other dimension at all. Suppose this is your X direction. Right? And let's say that you have some data point here. Let's say we are talking about horses and cows, because I suppose their weights will overlap. Right? So let us say that you have, a lot of data points. I'm raising it here, but they're all points along the, lots and lots of points here. Right? So let us imagine that the histogram or the frequency plot looks like this for a horse. Right? And let us take cows. The cows are pretty close in weight, right? And you would imagine that they would have a lot of overlap. So here we go. And so the cows go, actually, let me make the overlap more severe just to illustrate what we are talking. Actually, more than that, let me make this green line a bit more pronounced. Let us say that this is the, I seem to be making a mess here. This, and this is the horses. The data, the weight of the horses are all clustered here, right, in this region. And the weight of the cows are now, let us say that, you notice that now the data is overlapping because there are regions in which the cows and the horses are both exist. Isn't it? So this is the region in between that you see here, where both types of data exist, both cows and horses exist, right? And this is weight. Let's just take a weight. Does this make sense, guys? I hope this picture is intuitive. These are cows, right? No, cows. I should write it in blue. And what are these hills that I have made? These are just the histograms normalized. When you take a histogram and you divide it by the total total weight of all the horses and cows, they become what is called probability distributions. Right? A probability distribution is nothing but a histogram that has been normalized. So this is what you get, something. And by the way, that I'm being a hand waving there, a little bit approximate, but that is it. So this is where you are. So what is the weight that you find most horses to have? So you see that most horses have, this is your mu horse. the center of the average weight of the horse. And likewise, what is the average weight of the cows? Obviously, this goes like this. So the average weight of the cow is, this is mu cow. What does mu stand for?
Average.
Average, right? It's the average. So now think about it this way. I will put a red point and tell me what is it. Suppose I get a data point that is here. I'll call it A. I'll take a data point that is here, B. I'll take a data point that is here and here. I'll call it C, and I'll take a data point here. I'll call it D. Right? So tell me, in this diagram, if given this distribution, this common sense, at A, what would you guess it is? Is it a horse or a cow?
A horse.
It is much more likely to be a horse. There is a very vanishingly small probability that it may be a cow. But the reason for that is bell curves actually never go to zero, even though in this picture I seem to have made them go to zero. They always remain above the zero value. They never reach down to zero. So there is a vanishingly small probability, let's say 1 in a million, that it may still be a cow, but for all practical purposes, you are making a pretty safe bet when you say that A is a horse, right? So A, you can very confidently say, and you can say it with confidence. What about D? What is D?
D is more clearly a cow.
More clearly a cow. It's pretty certain, right? So you would say that you can make this thing with high confidence, high probability. Probability you're able to tell. Now, what about points B? B is more likely to be a cow or a horse? What is the point B? You know, it could be either, but it could be either. But if you had to make a bet, what would you say? Is it more probably a cow or more probably a horse?
More probably a horse.
More probably.
A heavy horse.
Probably horse. Yeah.
Heavy horse or light cow.
A horse, more likely to a horse, or maybe a rather emaciated and underfed cow. So on the other hand, a point C here, and this is what gets tricky. On point C, what do you think it is? Is it an overfed cow, or more likely, is it a cow or a rather obese horse?
C is more likely to be a cow.
It's more likely to be a cow, isn't it? More likely a cow. And so the question comes, you're going from very sure, if you go from A to B to C to D, as you go along the x-axis, you go across the spectrum of certainties. In the beginning, you're pretty sure it's a horse. Then you're less and less certain, but you're still saying horse. You reach B, you're still saying horse. By the time you reach C, you begin to say it's more likely a cow. And by the time you drift a little bit more, you become more and more certain that it is a cow. So you would imagine that there is an inflection point at which you sort of are sitting on the fence. You're not sure whether it's a cow or a horse. Where would you draw the inflection point? Would you draw it something like this? This line, isn't it? What you would do is you would take the point where they intersect and you would draw a line there, right there itself, at this point. And you would say that this region is horse. Oh, okay, let me make it a little bit bigger. This region is all horses. And this region is all cows. So once again, you have divided this line. The feature space is just a line in this place. You have divided the feature space into two regions, to the left of this white line and to the right of the white line. To the left are all horses, to the right are all cows. Now, what is the technical name for such a thing? Something that divides a feature space into partitions, one for each class. What do we call it?
Decision boundary.
Decision boundary.
decision boundary. Excellent. So this is our decision boundary.
Online class.
Now, let us generalize this to higher dimensions. Okay. Oh, my green line has. I hope I will achieve that.
So just go.
The green line somehow disappeared. Bring it in so that
That would be great.
we're talking about. We have to go through this. So here we go. And at this point, sorry, I'm just decision boundary. Now, before we continue, let's look at the implication of what we have just done. You realize that we will make mistakes. This region, this in-between region, is the region of mistakes. Do we agree, guys? This region. If I were to switch to a white background, look at the yellow part. This is the region where we are making mistakes, or are likely to make quite a bit of mistakes, actually. So this brings us to a situation where classifiers, okay, no, this is wrong. Let me go back to the color. So we realize some important fact. Classifiers, very much like regressors, classifiers have errors too. Isn't it? So what can happen is you can get confusing. The classifier may confuse a horse for a cow. They can, I'll just say, they can confuse a horse for a cow, or vice versa, right? They can have a cow as a horse. So let's make a matrix. We say that suppose in reality, it's a cow. A thing is either a cow or, just put it in full letters. Let us say that you know the ground truth, you know the answer, and you're asking a classifier to learn it. So, and then once the classifier has learned it, now remember, I'm putting hats on predictions. So what can happen? Good thing could be a cow could be marked as cow. Let's say that we have 100 instances of data, say 100 instances of data. Let us say that we got the cows and they're equally split between, and need not be equally split, but this is an example, between cows and horses. If you have a situation like this, so there are 50 cows, let us say that 50 out of the 50 cows, 40 of them were recognized as cows and 10 of them were mistaken to be horses by your classifier. And likewise, there are 50 horses. Let us say that about 35 of them were recognized as horse and about 15 of them were confused as cows. Are we together? Now, this is called, this view, it is called the confusion matrix. It's called confusion matrix. This term is a technical term and it needs, I hope it doesn't need much explaining. Why is it called confusion? Because it literally quantifies how confused the classifier gets in identifying cows and horses. Isn't it? So it got, how many of them did it get right out of the 100? Anybody? What is the
75.
75? So the correct ones are, correct is equal to 40 plus 35 is equal to 75. And the errors are, how many of them are wrong?
25.
10 plus 15 is equal to 25. So now, if I were to divide this with the total being accuracy is definition. This is the definition, basic definition. Accuracy is correct over total. How many total data points did we have? 100. So we have 0.75 or 75% is the accuracy. Now, what is the error rate? Errors. Error rate is defined as, sorry, by the way, this symbol mathematicians use to say, when you have two dots and an equal to, it is supposed to be the symbol for defined as. So error rate is defined as errors over a total. And so here it would be, 25 over 100, that is, so obviously 25 over 100, I'll just write it as 0.25, and that comes to, or other way people often speak about is 25% is the error rate. So it is obvious that accuracy plus error must come to 1. Does that seem obvious, guys? Plus errors is equal to 0. It must always be true. So either you are right or you are wrong. Right? The rate at which you are right and the rate at which you are wrong should add up to essentially 1. So these are definitions. This particular region, let me just say, these are definitions. So we should remember these definitions. This is error rate. Now, as we make progress, we will talk more about error rate. We will introduce concepts like precision and recall, but that will come later. Today, I would like to talk about something called true positive and true negative. Right? These are often called in literature type 1, type 2 errors, and so on and so forth. Lots of words are there. I will use more intuitive terms. So when you say true positive or true negative, I will illustrate it with a different example where we have the meaning of it becomes much more obvious. So let us say that today we are all worried about, let us say that a lab has a new COVID-19 test. No test is ever perfect. So what it does is it takes the data X, which is, I don't know, attributes in your saliva, or not the saliva, I believe they work with nasal swabs, right?
Yes.
Swabs. SWABS, right? Swabs. Attributes, some chemical attributes, biochemical attributes in your swabs. And I don't know the details, so I'll leave it as that. That is your X vector. That goes into this. What is Y? Y hat. Y hat belongs to the class of positive. Does have COVID-19, right? COVID-19. Or negative, healthy. Y, i.e., does not have COVID, does not seem to have COVID-19. Does not seem to have COVID-19. So this is a prediction. Any lab test, there's no lab test that is 100%. Every lab test is like a machine learning. It is a machine learning classifier of sorts. Because what you do at the end of it is you look for presence of certain reactions. These, from what I understand, I'm not a biologist, they look for something called polymerase chain reaction and things like that. Now, that is something I'll have to ask my wife because she's a molecular biologist with To me, it just sounds like a big fancy word. But in any case, it can do that. So now, if we do a confusion matrix for this classifier, detectors, classifiers are, their very nature is detectors in such situation. So let's think about it. This sort of a situation, this example, use another, highlight this point. This use case illustrates the asymmetry of data. Most people, do they have COVID or they don't have COVID? They would not have COVID, isn't it? The vast majority, at least we are still at the stage at which the positive test cases are far fewer than negative test cases. I believe they just released the data for Fremont that said out of approximately 900 something, let's take 1,000, 37 turned out positive. So that is a 3.7% positive rate. So what will the data have? It will be most of the data points with which you try to train your classifier, they would be negative. They would represent healthy people. So let us write symbols for it. If I were to write symbols for this, sorry, give me a second, guys. This thing has dropped off on me. Yeah. If we were to use symbols, we would say, let's use a symbol for positive has COVID, 19, and we will say, let's use a symbol. Let me just call it a positive case. This is a positive test case, right? Positive. And then does not have healthy. Healthy, negative. Now, you have a machine. It is a classifier that will predict has COVID, 90, prediction, healthy. So here, and I'll mention this point, sick people or sick or positive cases will be much fewer. Now, this seems obvious, but it has actually quite a bit of implication, basic implication that I would like to highlight. So now, let's take this example. Let us say that, God forbid, I hope the Fremont's test is not inaccurate, but it will have some level of inaccuracy. No test is ever perfect, right? So let's say that people who had COVID and you identified as COVID, there were 37. Let us say that people who did not have COVID and you identified correctly as not having COVID, let us say 900. I'm just throwing random numbers here. Right? Then we have now left about 63 cases. Let us say that out of 63 cases, we confused 50 people and said they are actually healthy when they have COVID. Let's say that they are at very early stages of it and your test couldn't find it. And let us say that you have 13 cases in which you declared a healthy person to have COVID, a test like that. Now you realize that mistakes in these situations are pretty bad. It's something to keep in mind. So sometimes, I'll just make a point, sometimes classifier mistakes can have devastating consequences. So, for example, another thing is, suppose you are being tested for cancer. We all go through cancer screening. As you get older, it becomes almost mandatory to regularly go through it. And I believe you go through it even from an earlier age. So, what is the worst thing that can happen? You have cancer and it is not caught in time. So if you're declared healthy when you do have cancer, it's not detected, then by the time it's detected, it becomes far more expensive, both in financially and in terms of suffering for the patient to cure the person or to bring the person back. And if you are too late, then it may be impossible to bring the person back at all. So one of the things to realize is certain mistakes can have devastating consequences. But then there is another aspect to that. The kind of mistakes matter. So let's think a little bit about what I mean here. Kind of mistakes matter. This mistake, I will highlight this or say, this is, what is it? Is it, we have identified a positive people as healthy. So this is this, I'll call it false negative because that is it, false negative, right? Because the person was sick and we did not identify the person as sick. Does the word false negative make sense to all of you?
Yes.
Yes. So it is false negative. And this, you would agree, is the opposite situation. It is the false positive. And this one is true positive. This is the happy situation in which your test caught it. Your classifier was able to tell the sick people as the sick people. And what is this? This is for
True negative.
true negative. Exactly. Thank you. True negative. So these words get it into your mind. But when you set a positive and negative, you have to ask yourself, which class should I consider the positive test case situation? Sometimes the domain experts will tell you what is a positive case, but but generally in the absence of information, one rule of thumb is whichever is the rarer situation, look into your data and look into your labels. Whichever label is less frequent is your positive case. So for example, in medical literature, this becomes pretty obvious. Positive cases are sick people because fortunately most people are not sick. So you mark a class as positive. In this case, COVID-19 has COVID-19. And then you have true positive means how good were you in catching the sick people as sick people? That is a happy situation. How good were you in identifying healthy people as healthy people, the not sick as not sick? That also is a happy situation. You want to have more of that. So this is your principal diagonal in this matrix, isn't it? In this matrix, this is your principal diagonal. But then everything perpendicular to that, off diagonal, are bad things. The first is false negative. A lot of sick people you marked as healthy. Why? Because if you mark them as healthy, as we know today, by the way, this is of quite a bit of contemporary relevance. We are having so many situations in which people were screened. For example, when you go for a COVID-19 test, the classifier sometimes, the first line of classifier is just a nurse or a medical expert asking you, did you just return from China? Or did you travel, or were you in contact with somebody who returned from China? And if you said no, they would say, well, in that case, you don't have COVID. You don't need to be tested. Go home. Now, was that a very accurate classifier? Was that a good classifier, guys?
Hmm.
No,
Not
no.
now.
Right? It was a health policy blunder to say like that. In hindsight, we know that it was it would be considered imbecile to have behaved like that. And the only thing you can say is the reason people behaved like that was because we simply did not have enough tests. So the tests had to be given to the most needy. Well, then that shifts the question, why did we not have enough tests? Well, that's a separate question. Certainly, as a classifier, it's a very poor classifier. As we all know, a lot of people had COVID, they got extremely sick and they died. So obviously we wouldn't consider that a very good classifier. Then comes a classifier that can do test. As you know, there was a test created in Germany and advocated by World Health Organizations and a lot of people. In Europe, it was used. In Singapore, it was used. It is being used, which is rapid testing based on two protein tests. It looks for two proteins that are found on the body of the COVID virus. We decided it shouldn't be used. Why? We are going to come up with a better test which has three proteins. Right? So why did we think that we need three proteins? Because we felt that it would miss some of the COVID cases. We needed a far more accurate. So now we are swinging the pendulum to the other extreme. We need a very, very sensitive test that catches all people who have COVID. The idea was that if the two proteins are not present, but it is still possible that you have COVID-19. You still have the virus. And so we were trying to get to a situation where we did not have false negatives. And that is still an ongoing effort. As of this moment, a much more sensitive test has not come. So people are still using after much ado, we all decided to go ahead and use the two protein test, which is being used at this particular moment. But it does highlight the point that would you, in a time like this, and these are real life decisions when you deploy a classifier in the field. Every classifier will have a false negative rate. Therefore, do you not deploy it at all? Or do you say, well, it is better than nothing? And so let's go ahead and deploy it till we come up with a better situation. And it's a policy decision. Which way would the country go? Different countries went different ways. The European countries, for example, they went ahead with the two, and much of the world went ahead with the two tests. In US, we believed we could actually come up with a much better test, and we thought, let's go and wait for a three protein test. And I'm not a biologist, but this is how I have been told the situation worked from the New York Times. And then it turned out that our third protein test was not accurate. So, well, it became a mess. And now they're trying to create yet another more sensitive test. And these are real things. In practical life, a classifier is never perfect. So you have to choose, is it worth using or not? And so those are the decisions that people face. Now, you also have the false positive. At this moment, a healthy person is declared to have a COVID, let's say. Now, which of the two is more dangerous, a false negative or a false positive?
False negative.
Positive.
False positive. Why is a false positive more dangerous?
Don't want to miss any case, sir.
No.
False negative is dangerous.
Negative is the most dangerous because you let one person that is infected.
You'll miss the sick person.
So the idea is that suppose you declare a healthy person to be sick. The person will get depressed and start getting scared, but will be quarantined. And in a few days, it will turn out the guy has recovered from the flu, right? And the fever and the flu, and it wasn't COVID. So it causes a nuisance. It sort of creates stress in the patient's life, but it is not fatal. So a false positive is not fatal in these situations, but a false negative can be fatal because if you miss a positive case, like you said, Sukma, then it is very, very dangerous. So you try to get a test which has very low false negative rate. And which is the hope, I suppose, which is why we went through this very interesting situation. The hope was that we could create a much better test with a higher false negative rate, and that is still work in progress. So false negative in this case makes sense. Likewise for cancer, what will happen? If you declare a healthy person, if you have a false positive, you declare a healthy person to potentially have cancer. The way, obviously, while you're a doctor, you don't rely on only one test. If something looks fishy in one test, then you do secondary, you do a sequence of tests. Well, some other test will after that, more intrusive test, will come out and say this person is totally healthy. So barring a small scar for biopsy, the damage is limited. On the other hand, if you tell a person with cancer that you are healthy and you don't follow up with that person with other tests, because there's no reason to, you have classified the person as healthy, then the price or the consequences can be very dramatic. So that is the concept of true positive, false positive, etc., etc. Now, there are words like precision, recall, etc. We will cover that next time, but for now, I won't, because let us digest this information in small bites. So let me recap what I said. Whenever a classifier makes predictions, its metric or measure of errors is done through a matrix, the confusion matrix. Why a matrix? Matrix is a grid of numbers. And that matrix is about, like this matrix here, true positives, true negatives, false positive, false negative. Right? And you attach the word positive, negative, and when by convention, you apply a meaning to that. Right? If you don't, then you just talk in terms of the confusion matrix and you just leave it as that. So there we go. That is the concept of positive and negative. So for example, now if we go back to our cows and horses, you realize that this region, this green region, is the region of mostly true, let's say that the horses are positive. This green region and this blue region, they are all regions of true horses and true cows being identified as cows. The in-between region here, the one that is highlighted in yellow, this is a region where we're likely to make mistakes, isn't it? And that is the region of most error for us. Because these two bell curves overlap. Now, what if they overlap even more? So let's take the limit in which two species of horses are there. Let's say that this is a horse and there is another species of horse. Oops, what just happened? Yes. Let's take another species of horse. I'll take blue, which has. Now, guys, talk about this. How accurate is this classifier going to be? Mu horse type 1, and this is horse type 2. Let us say this is some horse of type mu horse type 2. The mu is the mean, where this location and this location on the x-axis. And let us say that the axis is size of the horse, size of the horse. And it is quite possible. So it happens, when two species of horses are very near each other in sizes. So what will happen? It agrees with common intuition that you will have a pretty high error rate, isn't it? Do you see that the overlap region is pretty substantial? What should I say? This entire region, let me mark it this way. Let's say pretty significant overlap region. So what will happen is, let's make a decision boundary. Here is your, once again, you take the hilltops and you bisect it. So this region is horse type 1. This region is horse type 2. You realize that there will be a lot of horses, blue horses here, and there will be a lot of green horses here. So you will have high error rates or low error rates in this situation.
Hi.
High error rate.
So in discriminant analysis, the error rates are proportional, or geometrically they show up as the degree of overlap between the two bell hills or bell curves. Does that look pretty obvious, guys?
Yes.
I hope it looks straightforward, eh?
Yes.
Because it's very hard in the asymptotic limit. Right? Suppose we have asymptotic limit. Suppose you have a situation where you have a two bell curve. Let's say that you have a one like this and a two one like this. Do you think this classifier is even worth using?
Not much.
Not, right? Yeah, it basically means that whatever feature is here, feature is that you're using along which these two things overlap so widely is probably not a good feature if that is the only feature you're using. The input data does not give you enough differentiation between the two types. This is it. And the same thing can now be generalized to higher dimensions. In two dimensions, for example, the feature, if the Bell hills have a significant overlap, the error rates will be higher. Together. So this is all I have. I'll just let us go and recap what we learned. So we learned that geometrically, we can have overlapping data. When there's no overlapping data, for example, for ducks and cows, there is no sufficiently gigantic duck that you would confuse with a cow, and there is no minuscule cow that you will confuse with a duck. The two bell hills are very well separated. So a classifier works great, and it tells common sense. A duck you can carry in your hands. Most of us can't carry a cow in our hands. Maybe athletic people can carry a newborn calf. So the weights are quite different. Easy to classify just based on weight. Then in real life situations, it gets a little, from that very clean situation, it gets a little bit less clean. A horse and a cow now, if you only look at the weight, it might not be so easy to. By the way, any biologist, any zoologist here, am I right about horses and cows that they can have overlapping weights? Isn't that cows are way heavier than horses? I don't know. But let us assume, for the sake of our learning, that cows and horses have overlapping weights. Cow, when the in between region of rather big horses and rather small cows, you don't know whether it's a cow or a horse. So then you have error rates, quite pronounced error rates. And error rates, when you do, they come because a cow can be confused for a horse, or a horse can be confused for a cow. This representation of what happens, how well your classifier works, this is how you measure errors in classifier. And this is, by the way, one step towards the loss function pathway. There's a whole session we'll do next time on loss function. I'm keeping it for that, but I'm laying the groundwork here now. This is there. Now, the definition of accuracy is the number of correct predictions out of the total. And the error rate, which is the converse of it, is the amount of errors over the total, out of the total. So obviously in this situation, this contrived example, we have 75% accuracy and 25% error. Now let's take a situation in which data is skewed, they're highly asymmetric. The sick are few and healthy are many, for example, is a medical situation. We took the example of COVID-19 here. So what happens here? You can have a lot of people and this I think is somewhat, I just cooked up this data because I came to know that there were close to 100,000 cases tested in Fremont. And obviously I'm hoping that the error rates are not so bad, they're very low. I don't know what the real error rates are, but these are contrived examples. Do not treat it as a real life reflection of what's happening in Fremont. This is illustrative of a concept. So suppose, and 37, by the way, were the actual number of people who were found to be positive. So 37 that. And the rest of the example numbers are contrived. Let's say that 900 didn't truly have it, but, God forbid, but we had 50 as false negatives, people who did have it, but perhaps in such an early stage it wasn't called or whatever, and healthy people who were scared into the belief that they do have COVID. So then brings up the concept of false negative and false positive. False negative is when you take a sick person and you declare to be healthy. And you take a healthy person and you declare to be sick, that is a false positive. Now, we do know at least two methods that have been applied recently. One was just a questionnaire. Did you go to China or interact with somebody from China or travel abroad or something like that? If so, if not, then you're just declared to be healthy. You're sent home. We didn't have enough tests, so we had to ration it, the requirement. That as a classifier, is it a good classifier or a bad classifier?
Crude.
Anyway?
Too simplistic.
It's too simplistic. It's likely to have a high, what, false positive or false negative rate?
Not a false negative.
False negative.
False negative rate. And in medical situations, generally high false negative rates are heart rate. They have devastating
Bad.
And which is why you need a proper biochemical test, which has come now. Let's hope that the accuracy of the test is high and the error rate is low. And certainly what matters is not just error, but type of error. One type of error can be far more devastating than other type of error. A false negative has far worse consequences than a false positive. So all errors are not alike. In other words, some have deeper impact than others. And that is something to remember. Now, that is the summary of it. In the case of discriminant analysis, geometrically, the errors come from the overlap region between the two bell curves. Broadly, largely. There's always some overlap, but how degree of overlap? It is how much overlap there is at any given place determines the amount of errors that you will have. And the more the overlap, the worse the classifier will function. If you are going to use that particular feature to classify. In this case, the size of a horse. So there are two species of horse which are very close to each other. Probably you don't want to use the size or the weight as a metric. You probably want some other test, perhaps a genetic test to tell what it is, or maybe a color test. You know, maybe the two species of horses have different coloration. One is light brown and another is dark brown, and so forth. So, but size would not be a good predictor, a good feature to work with. That is that. Now, one last thing I would like to mention is, see, whenever you measure a model, the metrics of a model, how good is a model? Remember that in linear regression, we said that it's not enough to just look at R squared. You have to look at many things and make sure that they are right. You recall that, guys? Your residuals should show homoscedasticity, uniform in simple terms. They should you shouldn't see a pattern in your residuals. That is important, isn't it? You also look for good t statistics and so forth, and your p values and whatnot. But no one test should be taken as in and of itself a gold standard. It's not a litmus test. A lot of errors were done in many subjects because people over-fixated on p-values. If the p-value was sufficiently low, below 5%, they thought they have a result. They have a result of statistical significance. So a lot of research for many years had to be thrown out. We don't trust them anymore because of this fixation on p-values. Likewise, the same is true for R squared. I believe when we did the lab, we saw that in the case of dataset 2, the R squared turned out to be pretty good with a linear model. But then on further test, we realized that the residuals look pretty poor. They show a pattern, and that was bad. And so you have to have multiple things to tell whether a regressor is good or bad. You have to be very cautious. The first quality of a good data scientist is they are very cautious. Even when they have a good, they think they have a result, they're only cautiously optimistic. They're very free to admit a negative result, that we didn't succeed, but they are very cautious about saying that we may have something, a good result. Remember that as a basic habit. Never get too optimistic. There may still be things that you may get wrong. And in this field, it's quite interesting. If you are you're not careful in the early part of your career, sooner or later, someday, you'll make a grand ass of yourself. Everybody has done that. Because you would confidently say, I can see this, and then the very next day you'll find something, some data that completely destroys your model. And then in hindsight, you look back and say, I know, why this model worked, why it got fooled. And I wish I didn't express so much confidence to the business people that we have a good model. So remember that. So now coming to classifiers, what do we do? One of the measures that people get fixated on is accuracy. And many people say, I have a classifier or a test, and it is very accurate. So I want to speak a little bit about accuracy. Is this all we need? Because most people keep reporting on accuracy of the tests. And a test is always, is in a sense, a classifier. So let me ask you this question. Let us take this example of COVID, the same example. Suppose I have a magic box and you come to my testing center and I say that I have such a wonderful test that I can just look at you and tell whether you have COVID or not. And you believe it. You say, well, what is your accuracy? I say to you that my accuracy is actually pretty high. It is 93%. I mean, 91.3%. You would be pretty impressed. A test that is 91.3% accurate. You would say, well, I'm going to buy that test. So I'll pose this as a question. If I tell you that my test is 91.3% accurate, and it is indeed 91.3% accurate, no cheating there, lying out there, would you buy the test? So I want some people to think openly. Would you buy that test?
I think you want it better.
Well, 91.3 is pretty good, let us say. In the absence of anything else, let's say that the new medical test is still in scarcity a few weeks ago, and I open shop and say, hey, I have a way, all you need to do is come and show your face, and I can give you the result in 1 second. It's going to take 3-4 days, but my result is in 1 second. Results guaranteed with 91.3% accuracy. I do have some error rates, but I am 91.3%. And you say, well, wow, that looks pretty impressive, isn't it? Anybody would find a very obvious flaw in this?
Yeah.
What is that?
The test, I mean, it is still not on the test data, right? It is only on
Test data, cross-validation.
Trying to find a needle in a haystack.
That is right. So see, assume that I give you all the data to validate that my my results are accurate. I have a model and you can try it out on your test data. You have a private list of people who are sick and not sick, and then you send it to me, and then I make predictions. And lo and behold, it always turns out to be 91.3% accurate.
90% does not have any illness as such in the raw data. The accuracy has no meaning here. So.
Yes, is one answer. Anybody else would like to say?
Asif, I would like to understand, is it 91.3% true positive or true negative?
No. I am saying that my results, the accuracy it will have. What is the accuracy? The number of times that I will give you the right answer. You can test it out. You have a private list of known sick and healthy people. You send them to me, I'll make my prediction. Now you check how often was I right. I'm 91.3% right.
So it could be the null hypothesis also could be like 91, 92%. So how to?
The null hypothesis.
It's imbalanced.
See, all of you guys are getting to the right answer. You're all saying the right thing, but I want to hear it much more articulated from everyone. So guys, vocalize, think why accuracy is it's dangerous to just look at accuracy. And I'm not cheating. You can try out my method. In fact, today I'm willing to open a shop right now. Given this data, let's say that this data written in green is the data for Fremont. I can claim that I will have 91.3% accuracy based on this data. You can send your patient.
Say all are negative and you can get that.
You're trying to find such a small number.
Somebody said something. Who is that? All are negative. Yes. Yes.
You can say all of them are negative.
Yes.
You can
Right.
That if I have no real test, I look at everybody and then I give them a private slip and say, you can go home and look at whether you have it or not for reasons of privacy. I can't tell it you. Or I take this.
So Asif, can it be balanced and unbalanced because the classes of positive and negative is like, so
Yeah,
it is not that distribution is not.
See, Anil, you look at this data is imbalanced.
Are there enough classifiers?
Again?
Classifiers?
Okay, guys, I'll give you the answer now.
Class is so small.
See, guys,
you can express it in a way that if for the entire population, if 97% of it is actually infected, then if your test has to be more accurate, you need to be more accurate than 97.3% for that test to be relevant.
All of you are coming towards the right answer.
The recall.
Yeah. Here's the thing. Let's use. Suppose, like any other disease, most people don't have it. So I know from experience, or by looking at this data here, I know that about 87 people were sick and 913 people were healthy out of 1,000. So I know that 91.3 people are healthy. So all I do is I just look at a person, call them privately and say, now I'm going to disclose you your result, and then say you're totally healthy. Irrespective. Then what will happen? I will miss those 87 people. I will be wrong about those 87 people, and I would have declared 913 people who are healthy as healthy. My error rate will actually be low. My accuracy will be very high. But you realize that this classifier is of no use. Right? There is a reason why U.S. government is not lining outside my door to buy my classifier, isn't it? Because it is absolutely useless. Why is it useless? It is useless because it fails one fundamental test. It does not identify the true positives at all. But then you can do the opposite. Suppose I say that, all right, whosoever comes to me, I'll just look at him and say, that guy is sick. Right? Then what happens? My error rate goes up, but I never miss a positive test case, because to me, everybody is positive. That too is a fairly useless situation. Now, these things happen in real life. Right? For example, if you look at the stock market, and I'm sure many of you are in the equities market, and you keep reading the analysts and the commentators and all these pundits who make projection into the future. Amongst all of these, there'll always be one or two people who will tell you that they predicted the dot-com bust before anybody else could. They predicted the 2008 bust before anybody else could. And they have quite a reputation because of being the prophets of doom who could correctly predict the doom, but everybody else was optimistic. Can you guess why were they right? Anyone?
Because they predicted it every time, and once it got like true.
So if you do this, every time you keep predicting doom, well, of course we right when the doom comes, isn't it? When the markets crash, you will look like a prophet. That is what's wrong with these things. You know, the saying is that even a broken watch or a broken clock
It's right twice a day.
absolutely right twice a day, isn't it? Whereas your watch may actually never be absolutely right. It may be a couple of seconds ahead or behind the standard definition of time by the atomic clock of the US government, isn't it? But a broken watch will outdo that, outdo your watch. It will be absolutely right twice a day. So you have to watch out. To identify a good classifier, you need to look at many things. You need to look at accuracy. But first thing you do is you look at the class imbalance. You realize that out of 1,000 or out of 100, 91.3% people are healthy. So if your accuracy is nothing more than 91.3%, you're not really doing a good job. It needs to be better than that. Better than that is called the left. How much left you have over essentially no answer. This classifier, by the way, my classifier, is it absolutely useless? No, it is a perfectly good classifier, legitimate classifier in the sense that it is making fairly accurate predictions. You call it, there's a name for it in machine learning. It is called the zero R rule or the zero R classifier or the baseline classifier. In any problem, you need to first identify the baseline classifier over which we are trying to improve. So somewhat like in linear regression, you have the null hypothesis. In classification, you have the baseline classifier. Just find the majority class and always predict that. You're ignoring all the features. That's where the word zero R comes from. Zero R means none of the features you even bothered to look at. You didn't take the temperature of the patient. You didn't take their, whether they're coughing or whatnot. All you cared for is you declared the majority of people are healthy. You're declaring everybody as healthy. That is your baseline classifier with an accuracy of 91.3. Anything you do must improve upon that. Are we together? That is one. The other thing is you have to look at the types of errors, true positive and true negative. You have to ask which is more adverse. If you have to focus on improving one, which one would you improve? Now, generally what happens is that after a certain limit, it becomes a trade-off between true positive and true negative. You're not going to get any further accuracy. You can have one dial. You can choose to have more true positives or more true negatives. And that is something we will think about. Let's say that I will illustrate that with an example. Right? Suppose you have this situation. Where do we go? We go here. Let us say that horses are 10 times more expensive than a cow, which perhaps is true in this country. Or let's say that horses are 10 times or 100 times more expensive. And somebody is trying to sell you an animal and saying it is a horse. You realize that where would you rather make a mistake? In false positive or false negative?
False positive.
Right. You don't want to have a test that will confidently tell a cow to be a horse. You would rather make mistakes in which you missed a horse rather than be duped into buying a cow as a horse, right? If horses are 100 times more expensive. So one way to argue with that is you have to look at what your positive test case is. It's horse, and the kind of errors you're trying to make is you don't want to have false positives. Right? Just as in the case of illness, you don't want to have false negatives. So to not have false positive, what will you do? Where will your decision boundary be? You realize that you won't put the decision boundary where it is. You will instead perhaps put your decision boundary, if you want to avoid cows being considered horses, you would perhaps go as far as this. You see my dotted red line? Yeah. And you would say that anything more than the dotted red line, maybe there's a reasonable probability that it may be a cow, you would rather not buy. Does that make sense, guys?
Yes.
So by sliding your decision boundary backward and forward, you can control, you can minimize either the false positives or the false negatives. And this situation occurs with many classifiers. Moving one leads to lose the other, lose the battle with the other. Like it's a trade-off thing sometimes beyond a certain point. So that is something to remember about classifiers. So that is all about measuring the classifiers. So the answer to that is no. Look at class imbalance. Look at the adversity of the errors. So I'll put it, look at imbalance, compare results with the baseline classifier, and so decide which type of error is worse. Decide catastrophe. Perfect. These are the things, and then not only that, but also adjust the decision boundaries to minimize adverse type of errors, whichever error is adverse, right? Even at the cost, even at some cost of rise of the other type of error. So this summarizes it. This is important. Now we'll give some names. We'll talk about precision and recall, and we'll talk about different things in the later lecture. Today, I want to take a break. It's 1.5 hours now almost. Let's take a break before we go into the next topic, which will be another kind of classifier called logistic regression. Actually, let me draw a big line here. This is the end for this part, maybe even a big one. And then we talk about a new classifier, a logistic classifier. Logistic and regression. The word regression is unfortunate in this, because it confuses people. But you'll see why the word regression comes into that. We'll learn about a new type of classifier called the logistic regression classifier. Let's do that after a 20-minute break. Let's regroup at 9 o'clock, guys. I will pause the recording for a bit. So this is called logistic regression. The word regression is often confusing. It seems that we are doing regression, but actually no, it is a classifier with a sort of a confusing name. That's why I tend not to use the word regression. I just say logistic classifier. So what is a logistic classifier? The logistic classifier takes a entirely different worldview on the data. Remember, discriminant analysis said in the feature space, each of the classes are separated from each other. It may or may not be true. The ground truth may or may not agree with that underlying hypothesis that they are well separated. What if it is different? So I will contrive yet another example. I don't know how realistic it is. In fact, perhaps it's terribly unrealistic. But for the sake of learning, we will contrive that example. So suppose you have, let's take two kinds of fruits that look pretty similar to each other. We'll take blueberries. Let's take blueberries. And the axes are still the same. Let us say it is the weight or size and the weight, right? I'll call this the feature x1 and the feature x2. So a size is one feature, a weight is another, or you can pick your thing. And so let us say that the blueberries are small. These are data points for blueberries. And something like that. I'll just mark it. And again, remember that we are not trying to be biologically accurate. It is just a pedagogical representation. Imagine that it is like this. And let's take some berry whose weight is somewhat within the vicinity of a blueberry. What would that be? Blackberry, raspberry? What would be, if somebody knows that? Kate, what would be a berry whose weight is somewhat close to, but more than blueberry? Are you there, Kate? I think we lost Kate. So anybody could give a Glennis, would you have a name for a berry that's perhaps a little heavier than blueberry?
I can't think of anything.
What about raspberries? Are they heavier than blueberries?
Yeah, about approximately.
A little bit heavier. Okay, so we'll just assume. Okay, since we can't think of a better berry, I'll call it red berries. Lack of a better word. So they're blueberries and they are red berries, and God knows what those red berries are. But their characteristic is if you plot their sizes and they look like this. Something like this. This is a very contrived example. And then there are certain red berries which are small, and then you could have regions of overlap. Likewise, there are certain blueberries which can be large, and let us add some confusion. So guys, if I were to ask you that here, are the classes well separated? Does it meet the fundamental assumptions of the discriminant analysis, the hypothesis that the discriminant analysis makes about the underlying ground truth? Is it met? Are the two classes? What are the two classes? The blue berries, blue berry, and the red berry. These are the two classes. If you look at this picture in terms of size and weight, do you feel that they are well separated, completely? They don't seem to be, isn't it? There is a level of overlap. The second thing is, do they seem to form bell curve distribution? Like, are they looking like bell curves, or are they centered around places like a bell hill? These berries. Who would like to answer this question? Are all the blues clustered around some place, and are all the reds clustered around some?
They're clustered around size, right?
About size, there you see they occupy different regions of the feature space, all right. But do they say if I make a histogram?
It's not a balanced bell curve, but skewed.
is not a balanced bell curve, exactly. It is skewed. Right? So it seems to violate some of the assumptions of linear of the discriminant analysis. Right? And so this is something, the reason I mention it to you is that the ground truth may or may not agree with the fundamental assumptions of a given algorithm. So this logistic regression is an algorithm that shines in situations like this, where you see this. See, if I were to ask you this question, let me ask this question by putting a point somewhere. Let me put this point. Let me put this point A, a point B, a point, let us say, C, and a point D. What can you say about A, B, C, and D? A is what? Would you call it a blueberry?
Yes.
Blueberry, right? You would classify it as a blueberry, just visually looking at it. And D would be, what would D be? A red berry. And you're pretty confident, quite likely. Or very likely, let us just say, very likely. It is so. And what about B? Are you quite sure that it's a blueberry? Or you're less sure about it? Right? We are less sure, right? It's probably a blueberry, but as you notice, next to B is also a red dot. Right? So you're not quite sure it is or not. Probably a blueberry. And what about C? What is C? It is probably a what? A red berry, right? It's probably a red berry. So as you progress from A to B to B to D, I will make this arrow in this direction. You realize that progressively more confident that it is red, more probable, more likely that it is a red berry. Are we together? As you go from origin or from this point, as you go along this line, this is your line of increasing likelihood that it is a red berry. Would you agree, guys, with this statement? I hope you see this. It is quite obvious, right? And so, interesting thing is, what would be a good place to put a decision boundary? It will certainly be just along this line. Find a point where the likelihood is half and half between B and C somewhere, and draw a decision boundary like this. We'll draw a decision boundary. I hope I get this right. Where's the yellow? No, not this. This yellow. We'll draw a decision boundary. Does that make sense, guys? This would be our best decision boundary going through this. And let us mark it. This side has, and this side has red berry. Red, might as well. This side has red berry. So we have the feature space. Guys, I'm getting back. If you can please mute yourself if you're not speaking. Generally, if you do not have echoes, make sure that you have only one speaker attached to your laptop, either your headset. Or you mute your cell phone and use your headset, or remove your headset and then use the laptop. Then you won't get it. So, all right, here we are. We have partitioned this space, the feature space, once again into two halves. One region belongs to blueberries, another region belongs to the red berries. Isn't it, guys? And what is this decision boundary looking like? the decision boundary, let us look at its characteristic. The decision boundary, and I'll mention this, the in 2 dimensions. Suppose there were more features, it would become a plane in a 3 dimension. It is like, it's a linear decision boundary, i.e. the decision boundary is straight or linear. Straight or linear. That is its defining quality, the way we have drawn it. In this model, logistic regression way of looking at the world view, the world, and it is a hyperplane in 4+ dimensions. Anything more than 3 dimensions, it will be a hyperplane. A hyperplane is a generalization of a plane. It just is a plane in higher dimensions. Mathematicians can, this generalization comes very easily, though for our mind to visualize a hyperplane is a little bit hard. But just think of a plane and then imagine that it is mysteriously, there are more axes to it than just 2 axes to it. So that's a hyperplane. Mathematically, it works out. Human beings find it a little bit hard to sort of understand. So are we together so far, guys? What I will do is I will take this region, this picture, and I'll reproduce it below because I want to give you a sense of how these things work. So I'm going to make a much bigger drawing of this. And I'll put fewer points of the blueberry, and so that we have less clutter. Just assume that it is the same picture, but you have in red lines. This region is there. And of course, there are a few errors on both sides. This is your decision line, isn't it? Now, if I take an arbitrary point, let me take an arbitrary point. That point would be, let me take this point. Now, I'll introduce some vector notation. See, this one is a x1 direction. This is a x2 direction. So you agree that associated with point P, I can write some x1, x2 of that point P, isn't it? The point P has some xy, x1, x2 coordinates. Does that look simple, guys? Which will be wherever it touches the x and y axis, the x1, x2 axis. Y here is called x2. Do we agree, right? A point in a plane has a coordinate, has certain coordinates. If you have forgotten your coordinate geometry, you can think of it as longitude and latitude. Every point in this has a longitude, latitude, roughly speaking, a way of thinking. Now the question is, how confident you are that it is a red berry, probability of a red berry, right? How likely is it that it is a red berry? You realize that one thing that matters is this thing. This I will call the distance. D of x, this point, or D of point P, let me just call it D of point P, D of point P is, we'll define it as distance, and by distance it is always shortest distance. It is implicit, shortest distance. So when people in this field talk about distance, implicit it is that most of the time, unless stated otherwise, they are looking for the shortest distance from the decision boundary. Now, why is this distance d important? you would agree that if D is 0, then you're sitting on the decision boundary. So which is more likely? Is it more likely that it's a blueberry or it's a red berry? What would you say, guys? No, you can't say anything, no? It is the inflection point between blueberries and red berries. They're literally sitting at halfway point between.
Oh, if it is D is 0, then I say. Okay.
Let me mark it with a point here. Let me take a point. Let me call this point, what should we call it? E. So E is on the decision boundary. So what is the probability that the data point E is a blueberry or a red berry? You would say that, you would say that the probability of E by definition is half, that it's a red berry, isn't it? It is equally likely to be a blueberry. That is the literal definition of a decision boundary, because by definition, on this side it's blue, on this side it is red. Do you see that, guys? Huh? And so there is a point at which you're not sure whether it is blue or red. It's literally sitting on the decision boundary. Right? So the intuition here is that D is equal to 0 means on the decision boundary. On the boundary, so equally likely. Equally likely to be either. On the other hand, D greater than 0, what does it mean? If D is greater than 0, if you are somewhere here, like for example, for the point E or P, should I give P a new color? Maybe. Let us say point P. What can you say about point P? Is it red berry, or is it more likely to be red berry or blueberry? You would agree that D is greater than 0, more likely to be a red berry. And D is, we'll take the convention that if you are on the lower side of the decision boundary, if, for example, for a point, let me take a point, this. This point is, let me call it Q. Q is at a negative distance, negative D prime. So D, let me call this distance D prime, or DQ, DQ. DQ is negative by convention because you take one direction to be positive and the other direction to be negative. Right? So this is, you say that DQ is less than 0. So in the case of DQ less than 0, what can you say? The point is what? Is it a blueberry or a red berry? Right? Let me know if I need to repeat this. Huh? I hope this is fairly obvious. Huh? If I take this point, this is clearly a blueberry. No? It's where blueberries are surrounded by blueberries. It is light, it is small, and therefore it's a blueberry, more likely to be a blueberry. Right. So this is it. So in other words, we have come up with a way to classify. Use this distance function. In other words, this is an important observation. In other words, geometrically, we can use the, and now I'll give a name to this, a sort of a known name, use the distance function. To help us decide whether it is more likely to be red berry or blue berry. Right? This distance function. And this distance function has a definition, distance function of any arbitrary point x. Now I will use x could be any arbitrary point. The word arbitrary is often used in mathematics. It means that you just pick a point with nothing in particular about it, nothing special about it, any random point. So people don't use the word random, they tend to use the word arbitrary point in mathematics. Any arbitrary point, x is any arbitrary point. So x is basically the x1, x2 coordinates of this point. I'm writing it as in this notation, and from school you may be used to this one, x1 I plus x2 j. Remember vector notation? You may be familiar. It is all the same. It is just conventions of writing it. So a point, given a point, then you can find the distance from the decision boundary, dx. Now, here comes something, now comes an intuition that we have to develop, and this is the crucial intuition. As d increases, you know that it becomes probable that it is a red. Let's think in terms of probability. Probability, we will now think of probability. Specifically, we'll choose one, red berry. Red berry. Of red berry. This is the probability of a red berry. And this probability of a red berry, we will write as P. P, the P of X is the probability that a data point X belongs to a red berry. That is what we are. Now, a basic primer on probability. Probabilities go from 0 to 1. This is something mathematicians have defined, that probabilities are 0 to 1. Probability of 0 means it is quite likely, it's certainly not a red berry. Probability 1 is that it is a red berry. And then in between values are degrees of likeliness that it is a red berry. Right? So that is the definition of probability. P always belongs to P, X belongs to the interval. This epsilon stands for belong to. It's not the error symbol. Right? People often use the symbol. Let me use it as a big thing. They often use like this. So why is, sorry guys, my hand is coming in. Give me 1 second. I think, this writing pad is touch sensitive and I need to disable the touch sensitivity because my hand is coming in the way. So give me a moment. Sensitivity I do have device to function. I don't seem to have. Maybe to in the calibrate. But I am not able to find the right knob to turn off the options. Okay, here we go. Hold disable all tablet instruments, rockers, etc. Second tab. All right, guys. So we won't waste time here. I'll figure it out later. But somehow my hand touch is affecting this. So this is the thing. Probabilities go from 0 to 1. Now let's try to relate px to d of x. You realize that there is some relationship. As the distance increases, and let's look back at this figure, you realize that as the distance becomes more and more positive, the probability that it is a red berry, does it increase or decrease?
Increase.
Increase, right? In fact, when d is 0, you want the probability to be half. Beyond 0, you want the probability to continue to increase from half all the way to 1. On the other hand, when you go in the negative direction, when you go from d is equal to 0, which is at half, to d in this negative direction, how far you can get? Well, theoretically, you can go to infinite, d is equal to minus infinity, except that in real life, there are no negative weight and negative size berries. But okay, let's take it this way. Take it like that as a theoretical exercise, thought exercise, that when d becomes more and more negative, the probability gets closer and closer to what value? The probability of it being a red berry?
0. So blueberries.
Closer to 0. So there is an interesting parallel here. We do know that we have latched upon the right thing. This is the right way. Right? As dx tends to infinity, px tends to 1. As dx tends to minus infinity, negative direction, this tends to 0. Right? And also we have a px is equal to half when dx is equal to 0. Right? In other words, when you're sitting on the decision boundary, the probability is equally on both sides. It could be blueberry or red berry. Right? So now what we do, and we are going to think like people who are building up the whole a classifier from scratch. Right? How would you do that? You realize there's a problem. D belongs to the domain. D belongs to the domain minus infinity to plus infinity. P belongs to the domain 0 to 1. But we do know that as one increases, the other also increases monotonically. We just need to figure out a formula of P in terms of D. Right? In other words, we need to say P x is some function of d of x. Right? We do know that because as d increases, p increases, but what function it is. So let's try to worry about this central problem. D goes from minus infinity to plus infinity. P only goes from 0 to 1. So let's see if we can do better. It turns out that people who gamble a lot in horse racing and so forth, and people in common language, when they say what is the likelihood of rain, what's the likelihood that somebody would show up and so forth, they use not the word probability, they use the word likelihood. Likelihood or actually not even odds. Let me use the log odds. Odds. I won't use the word likelihood. Have you heard people talk about the odds? The odds that for example, this horse will win is 10 to 1. Some horse that is favorite and everybody has confidence. People will say odds are 10, right? Or 10 to 1, or the odds are very low, they're close to 0, and so forth. So odds tend to go from 0 to infinity. Like somebody says that the odds of my horse winning is 1,000,000 to 1. Right? They are saying they're very confident that a horse is going to win, isn't it? Or for example, if you ask this question, what are the odds that we can have perfect global warming? Right? So depends upon who you are. Some people will say the odds of a catastrophic global warming are 1,000,000 to 1. They're pretty sure it's going to happen. Other people will say, no, I'm not really sure. I would put the odds pretty low that there will be global warming, catastrophic warming or something like that. So people differ on their perception. Talk in terms of odds. Usually you don't find common people talk in terms of probability, etc., where probability goes from 0 to 1. So what is the definition of odds? Odds is, it turns out, odds is defined as the probability of something over the probability of its not happening. P over Q. Q is 1 minus P, not happening, the probability of not happening. So, for example, in the case of a horse, P is the probability that the horse will win. Q is the probability that the horse will lose. So that is called the odds. And because Q is 1 minus P, odds are a P 1 minus P. So in case of a blueberry, red berry situation, it is P is a function of X somehow of the feature space. So you'd say that odds are this. Now let's study the odds. What does the function, the odds thing, let me use a variable or a something for odds. Let me call it a symbol. Let me use a symbol O of X. Odds, right? Which is by definition probability of winning over probability of it being a red berry versus probability of it being a blueberry. Now let's study odds. We know that P goes from, Px goes from, belongs to 0 to 1. Dx belongs to, so this writing thing is coming in here. Dx belongs to minus infinity to plus infinity. What about odds of X? Odds of X. See, let's think about it. When probability is 0, 0 over 1 minus 0 is equal to? What is it equal to, guys? 0 over 1 is equal to?
0.
So it goes from the interval 0. And when probability tends to 1, like let's say that probability of something happening is 0.999999. So this is close to 1, and the denominator 1 minus something almost 1 is equal to what? A very small number, 0.0001. So now when you divide 1 by a very small number, what do you get? You get a very large number. You get something that's closer to infinity. So the domain of the odds is from 0 to infinity. Well, that seems to be an improvement. We have somehow constructed from Px something. If you look at this, it is a little bit more like dx, isn't it? The odds are a little bit like dx. Now you say that, well, we are almost there in creating a relationship between probability and distance. We do know, we are trying to infer what this function could be. Now comes this thing that there is still the problem that this goes from minus infinity to infinity and this goes from 0 to infinity. Once you face this problem, now you have to use a bit of a trick. This trick, it turns out that people who are savvy with mathematics, they know it. If you want to convert something that only stays positive, you notice that this only stays positive. There is actually a very easy way to do that. You do this. So I'll give you a basic mathematical trick. You take any number, let's say that x goes from any number. Think of e to the x. What happens when x is positive? When x is positive, e to the x will be what? Will it be positive? It will be positive, right?
Yes.
Positive. And generally, it will be greater than, it will be something, right? When x is, let's say, negative 10, what about e to the minus 10? Is it positive or negative?
It's positive.
It is still positive. It will be very small, but it will be positive, isn't it? Right? So this looks like a good trick. If we could take the distance and we do e to the dx, now what happens? E to the dx will go from e to the minus infinity is what? What is e to the minus infinity? That is equal to 1 over e to the infinity. And that is equal to 1 over a very, very, very large number is equal to
0.
It goes from 0 to, of course, e to the power infinity, of course, is infinity. Right? It goes to infinity. Now you see, we have a lovely thing. We realize that this guy and this guy, they behave exactly the same. Do you see this, guys? The odds behaves like e to the exponentiation of dx. And once you see that, this is when a mathematician says a moment of epiphany or a moment of discovery. You really get excited because you have found a very simple way of relating the probability to this. So you therefore make a theory. Let's invent a theory. We say, I suppose this requires, what just happened? Yeah, it requires a new color, perhaps. Let's use a new color. We will say that maybe odds of x is equal to, up to a proportionality constant, but why bother about proportionality constants? E to the d of x. Are we together? Suppose we do this. This agrees with our intuition, if you look at it. The intuition that as d increases, odds increase. Isn't it, guys? If you go and look at this, as d increases, as you go more and more towards positive direction, let me mark the direction like this. As d increasing, odds increase. Right? P increases. And P increases and the D and the increases. So we write this theory. Right? This is so lovely, actually, to find a relationship that is so simple. And if you do this, what you have just discovered is a very, very powerful equation in mathematics that is used all over the place. It's used in, population studies. I mean, one of the most fundamental equations in mathematics, applied mathematics, is this equation. It is called the logistic equation. And its utilization, and I'll tell you all the use cases that it comes to. But let us write it down. What was O of x? It was a P of x divided by 1 minus P of x. Isn't it, guys? Is equal to e to the d of x. This is our foundational equation, writing it back in terms of a P and this. And there are many forms you can derive from that. For example, you can say log of Px 1 minus Px is equal to dx. In other words, distance is the log of this odds, log odds. So in simple terms, d of x is the log odds. This is an intuitive way to remember that as d increases, the log odds of it being a red berry increases. Right? And now this can also be written. Let's see, you have this equation also reformulating. Reformulating it as is that. So you have, if you solve this equation, Px 1 minus Px is equal to e to the x, e to the dx. Oh, no, sorry. Yeah, e to the dx. Right? If you write this, and then what do you do? Suppose you add Px to the numerator to the denominator in both the situations. you will realize that this equation becomes, what does it become? Sorry, let me write it clearly here. E to the dx. Suppose you add numerator to the denominator, which is perfectly legitimate, so long as you do it to both sides. You will realize that px is equal to e to the dx 1 plus rather e to the dx. Do you see this, guys? From this, you can solve your way to this simply by adding the numerator to the denominator. Right? And this is the same if you divide both the numerator and the denominator by e to the dx, it will become 1 plus like e to the minus dx. Are we together? You can write it in this. And this is the form that is much more commonly found. Now, I use the word d for distance. Generally, in books, you find d of x called z of x or just z. What I call d, because to me it is very intuitively the distance function. It is in fact not just to me, it is acknowledged, it's known in the field to be the distance function. But by convention, people often write it as zx or just z. And so the common form that you find in books is p of x is equal to 1 plus e to the minus z. And I'll just write it as z here, of z of x is implicit. Z of x. Let me just write it in the form that you often find it in books, where z is equal to d of x, right? It's understood. This is the way, the typical form of the logistic equation. Logistic equation. Now, I'm going to spend the next half hour probing into this very, very interesting equation and making it down to earth, making it very real for you guys. But do you see what happens, guys, is that when you open a textbook in machine learning, they will start right away with this equation. Like, for example, your textbook ISLR, it starts with this equation. It is really worth asking, where in the world did somebody, where did equation come from? How did somebody think of it from first principles? And why should I believe this equation? And I hope I've given you the foundational understanding of where this equation comes from by looking at this example. Are we together, guys? I hope this becomes clear. Now, there is one little thing that I haven't mentioned. I'll keep it perhaps for next time today. We may not get time. That d of x is the equation of a straight line. Decision boundary, let me write it now. D of x, i.e. the equation for the decision boundary it is actually can be written, it is a straight line, represents, it's really mangling it up, represents a straight line or hyperplane. So equation of a straight line obviously is beta naught plus beta 1 x1 plus beta 2 x2. And where this comes from, and then you can generalize it to higher dimensions to that. This is it. Now, derivation of this will be in the extra session because it sort of gets a little mathsy, and you may or may not be interested with it if you're a person who's only caring about focused on the practical application. Let's say you don't need to know this. So those people who are excited about understanding how did this whole thing happen, we will cover it in the extra session. For the rest of it, just take it on trust that it is actually so.
Asif, one question.
Yes.
So It's two-parter. So why exactly? Why did we use EX? Why not just any other number? Why not pi raised to
Very
x?
good. It's a very good question. See, what happens is you look for the simplest thing available to you. Now, if you are savvy with exponentials and your algebra and so forth, the most natural thing that comes when you want to convert something that goes from minus infinity to infinity down to only positive part of the real of the number line, one easiest way is to just exponentiate it. If you try to think, you may be able to think of other functions too, but by far, e to the x would be the simplest that will come to your mind. And can you use other functions? By all means. This we are just making the simplest theory. There are other theories, and so they make for other classifiers.
And the second question is, why did we choose equal to? I mean, it should be proportional to, right?
Proportionality, you could do that, but you know, odds. The trouble with odds is it's just a number. So suppose you put a proportionality constant, you can just redefine your odds to absorb that proportionality constant. Because the point is odds vary in proportion to p the distance, right? Log of odds vary in proportion. So you just say that it's proportional. What happens if I set the proportionality constant to 1? I'll just end up redefining my notion of odds a little bit, or my notion of distance a little bit. Right? So you just absorb it.
Won't they affect the classification then?
No, it doesn't affect the classification. So since you asked that question, it's a mathematical trick. And those of you who are not very into, so let's say that we said log odds, right, is proportional to D. Odds is proportional to the e to the power D. Right? And suppose I did this, odds is equal to, therefore, let me just write it as odds one. Odds, right, of x is proportional to D of x. And so therefore, odd of x, to your point, is very simple to see this, is equal to some proportionality constant, right, e to the d of x, isn't it? Yeah. And now lambda I can write as exponentiation of some other constant, e to the, not lambda, but let me just call it some value, let me call it some constant c. Right? I can write lambda as e to the c, some proportionality constant. And so it will become e to the dx. And so what we are saying is odds of x is equal to e to the dx plus c. Right? Now what does dx plus c do? It just shifts the line. It just adds a constant to that, which is not terribly useful. Right? It just moves the line a little bit. That is why you don't care for the proportionality constant. And the simplest way is just set lambda is equal to 1 or c is equal to 0. And you end up with a simple theory. To summarize, we have this lovely equation which says that the probability that it is a blueberry, that this point is a, let me put it this way, probability that x in feature space is a red berry, rather, let me not confuse it, red berry is equal to d of x, which is the same as, now when I expand the value of d, e to the minus beta naught minus beta 1 x1 minus beta 2 x2. Right? So this is it, or rather, if I just put all the minuses together, it will be this. And this is also written as e to the minus z. It is the famous logistic equation. Now, this discovery of a logistic equation, I've literally taken you, I hope, through a process of discovery from first principles. What does this function look like? If you plot it on a line, on a graph, what does the logistic equation look like? It turns out that it showed up here, but it shows up at countless other places, and it has a very interesting look to it. So this is how it looks. Well, let me just put it this way. This is 0. So what happens is you realize that when x is minus infinity, this will be 0. Right? The logistic thing will be, oh goodness, this is a pain. What do I do to this? Okay, I'll just use the yellow line. It is here, very small. When x is infinity, this is probability, P of x. P of x can, the maximum value it can achieve is 1. So the minimum value it can achieve is 0. We realize that the maximum value that it can achieve is 1. And in between, it will rise up slowly like this. Now, this is what the logistic function looks like. This function has some very interesting qualities to it. First of all, needless to say, it is a continuous function. Let's look at its quality. The mathematicians like to describe it by qualities, continuous. It is smooth. Would you agree that there is no reason why it should be jerky? It is smooth. Any doubts, guys? It is smooth. The smooth word in mathematically means it's differentiable, means you can find the derivative everywhere of this function. But forget about that if you are not interested in that, the calculus aspect of it. But just notice that it is smooth. The other thing it has is monotonically increasing. Monotonically increasing. Do you see that, guys? That as x increases, it keeps on increasing. What would be monotonic means? It only moves in one direction, does not move in the other direction. So for example, as x increases, at no point does it start decreasing. It always keeps increasing. Right? If it increases, it always increases. If it decreases, it always decreases. That's the nature of monotonic function. Here it is monotonically increasing. It's a quality, isn't it? And lastly, has negative saturation point at 0. Right? This is also called lower. This is your lower asymptote. The mathematicians use a lovely word, asymptote. Right? So you see this, right? That as x goes to minus infinity, this probability of x doesn't budge much, right? It sort of saturates at 0. You see this, guys, in this region, it saturates at 0. 0. Right? So this is a lower asymptote. And what about this point? At this point, when x tends to infinity, does it again saturate? It again has a saturation point that is, has positive saturation point, positive x saturation, negative x saturation. Saturation point at p is equal to 1. This is your upper asymptote. And people who are used to the mathematical language, they will say that the logistic function asymptotes on the lower side to 0 and on the upper side to 1. It has lower and upper asymptotes. Now, it turns out, and something peculiar I'll tell you, or a way to remember. Think of this as S. Notice that it looks like a S stretched out. If you pull this and this in the other directions, stretched out, isn't it? To this. Does it look like this, guys? A stretched out S? Do you see that, guys? Or I would like some confirmation that this is very obvious. You take an S and you sort of stretch it out horizontally, pull in opposite directions at the tips, and it will begin to look like this. Do you see that, guys? Is it obvious? It is obvious, right? So it turns out that all such functions that look like stretched out S, right, and have the properties of being continuous, smooth, monotonic, and with upper and lower asymptotes are called sigmoid functions. Are called sigmoid functions. Are we together? These are called sigmoid functions. And therefore, logistic function is an example of the sigmoid family of functions. Are we together? Now, this, by the way, is a big statement because it will haunt you for the rest of your career in machine learning. It's used everywhere. The sigmoid functions are everywhere. Logistic is only one of them. If you try to plot tan H, you will realize that that also looks like that. There are quite a few functions that look like that. If you take the integral of the bell curve, to your surprise, the integral of the bell curve will also look like that. Right? There are many, many such functions. So let me illustrate that. See, a bell curve looks like this. Right? Now look at the error function, the integral of the bell curve 0 to x of e to the minus bell curve function is e squared over 2. This is the bell curve with approximate, some proportionality constant of 2 pi squared. So just take this fact, this as a thing, and you will realize that what happens is you're looking at the area under the curve up to some value x. So when x is minus infinity, what is the area under the curve? It's 0, isn't it? There is no area under the curve. Yeah, it is 0. And when x is equal to plus infinity, the total area, whatever it is, it will saturate to that, because you realize that after a certain limit, the area that is behind it does not increase, right? It saturates. So this function also shows a behavior that is like this, sigmoid kind of a behavior. Let me make it look more sigmoidal. So logistic is not the only sigmoid function. There are many sigmoid functions. They are all around you, the sigmoid functions, and they are very, very useful. The whole theory of logistic regression is one of the most powerful classifiers in the sense that it's interpretable, it's simple, and it is ubiquitously used. And when it works, we love it. Right? Many times it doesn't work. It's a simpler model, but the more complex models are actually built out of it. In fact, what today the state of the art is something called deep learning, deep neural nets. And one of the interesting things is deep neural nets are built, at least one family of deep neural nets are built out of sigmoid functions or logistic function. So today you've got introduced to one of the big pillars of machine learning, right? I took you through this intellectual journey and I took you through this derivation. By the way, I've never seen this derivation explained in textbooks, but I thought I will explain it from first principles because it is such an important part of the whole field of machine learning. If you didn't quite like it, if you're very practical minded, then please forgive this mathematical digression. And if you do like mathematics, it's really fun to know, what is it that drives all these neural networks and a lot of machine learning? What function is it? Where did it come from? It's sort of really worth knowing about this. So this is a logistic, many things. For example, in your nerves, right, the activation of the nerve-to-nerve communication happens through a sigmoid function. The signal transduction within a nerve itself is an activation function. So logistic or sigmoids are also called, logistic is also an example, also called activation function. There are many activation functions. Sigmoid, the logistic is one of them, activation function. What it means is, and there are many uses of it. For example, if you think of a transistor, those of you who remember your transistor theory, imagine that you have a positive charge. I don't know how many of you remember, and this is the ground. This is the bias. What happens? When the bias voltage is low, no current flows through. Low bias or negative bias, no current. After a certain value, some bias, current begins to flow through. Right? High bias, this is called a transistor. A transistor goes from when bias is low, no current flows through. Things that don't allow currents to flow through are called, what are they called? Non-conductors. Non-conductor of electricity. And high bias, current flows through, fully flows through. So it has become a conductor. And therefore the word semiconductor, it is something that is both a conductor and a non-conductor. It's sort of half conductor, just based upon the bias, right? That is where the words come from. And transistor, as you know, is the fundamental building block, is the atom of electronics, of computers. At the fundamental level, is the transistor that drives all logic. Right? And there it is, you have the logistic function. If you look at the bias voltage and you look at the current going through, it will again show you a sigmoid function or a sigmoid shape. And those of you who come from, how many of you have an electronics background? If you remember, this is how a transistor works. Right? Your nerve currents work like that. They also have an activation. Populations of species work like that. So for example, you can talk about how much risk, like what happens to a population. Let's say that this is time, or this is a time. A population will start very low of a species. If you throw them at an island, it will grow, 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 and it will saturate. Why? Why will it saturate? Well, the theory is that after a little while, any ecosystem can only support so many rabbits, let's say. So it will go, or so many people. So the population will saturate. So this is the logistic population model. So as you can see, this logistic function, it has many, many uses. In fact, if I remember right, the history of it is that it was called logistic because it also describes the literal logistics of armies during war, logistics of things and so forth. It is applicable there also. So many, many places it is applicable. So now, what does it have to do with the classifier? What it means is, suppose you can find the probability that it is a red berry. What you can do is you can make a decision. Probability of red berry greater than 0.5 means classify the point the point as red berry. P less than 0.5 greater than equal to blueberry. Right? In other words, the decision boundary is there. And this number is called the cutoff. That helps you decide. Right? Now, cutoffs are important. There's one more point I would like to make cutoff in the last few minutes. See, what happens is that cutoff is your choice. For example, if you are looking at somebody having a cancer or not, and you have a test, you have a classifier, a person who has a 50% chance of having cancer, would you call him as a positive or a negative case for cancer?
Too
It's a
high.
good question. What would you do? If a doctor told you you have 50% chance that you have cancer, would you act upon it or would you just sit there? Act upon it, because the consequences of not acting upon it are very drastic, right? So the cutoff that you choose, it depends on the context. So for example, for cancer detection or something like that, for cancer or very serious issues or other serious issues. So for example, if you have a certain probability model that a certain public transit system is going to be attacked, you won't wait for a probability of half, 50% chance that yes, it will be attacked before you take action, preventative action. What will you do? You will go on hyperdrive and security measures at fairly low probabilities. The cutoff in such situations can be as little as 10%. Even if there's a 10% probability or even a 1% probability, you want to say that it's a positive case. It needs further study. And that is what happens in medical practices. Any one test, if it comes out even a little bit positive, you do indicate it as positive probability. There are certain cutoffs, and then you send it for further study. You send the patients to further testing. Right? In security modeling, again, the thresholds are very low. Right? So where you put the threshold completely depends on you. I'll make it real for you with another financial example. So let us say that you all have children, and I'm sure that you all have been saving to send your children to college. One fine day, a friend of yours comes and says, hey, I've lost my job. And, I'm going through hard times, and could you lend me some money? Well, you are a good friend. You say, well, sure. And you're thinking of something like a few $100 or $1,000, $250,000 or $500,000 or something like that. A pretty large number. Now you're a bit shocked because that is the total pile of money, let us say, you have saved for your children's education. Right? And perhaps it's also all that you have for your retirement and so forth. It's a lot of money. Now the question comes, well, he's your friend. You would like to help him. At what probability will you give him the money? Right? If you are 100% sure he'll return it, you would give him the money. I suppose you would be a good friend. But then we all have different tolerances for risk. You would agree that if there is a 50-50 chance that he'll return it, you would be very hesitant to give it. You wouldn't give it to him. On the other hand, you would probably want assurance that is in the high 90s that your money is coming back, right? Because it is the only nest egg you have that you have, or the savings you have for your children and for your retirement and so forth. Right? So where you put the cutoff in a classifier to give him the money or not, or to probability that he will return, at what point you classify that yes, he will return versus he'll default. He won't be able to return. Right? He won't succeed or he won't be able to return. So depends upon, for medical situations or cancer, you would put the cutoff very low, maybe at 1% or 2% or 5%. Right? Or even if there's a slightest chance you may have a debilitating disease or terminal disease, you want to indicate it right away. On the other hand, for certain situations, you need absolute surety before you say it's a positive case. You would want to loan money to somebody only if that's the only money you have, you would want to loan it to the other person only if the probability that you'll get it back is in the high 90s. Right? And that illustrates the fact that cutoff and where you put it is rather problem dependent. The problem that you're trying to solve, it depends on that problem. There's something to know about probabilities, that when you use probabilities, which are continuous numbers between 0 and 1, and you make a classifier out of it, you have to choose a cutoff. In the absence of all information, you can take, for example, blueberry, redberry, it doesn't matter. Half is a good number. But in all other situations, you have to be context aware. What is the context you're looking at? Where should you put the cutoff? Are we together, guys? And with that, I will end this. Now, one more thing about cutoff is, this cutoff, right? Sometimes you can keep it at half, but you just have to move your decision boundaries up and down such that it serves your purpose. Right? So there are many ways, many knobs to play with it. We'll see it practically. You can insist on probability half always being there, but then how you move your decision boundary up and down so that you always get good results is an interesting game. We'll play that. We'll learn to play that. We'll leave it as that. Any questions, guys? Anything?
As if we started this with taking two input feature classes, right? All the things that we did would still apply the multiple classes as well.
Actually, it works for binary. You can. It only works for cows and ducks. You can't bring in a horse. If you bring in a horse, you have to play a game. One versus. So what you do is you three models. Probability that it is a probability that it's a and probability a duck versus not. And then you find out probabilities is the highest. If it turns out that the duck,
Can you please mute?
So I'll repeat it. What you do is one versus rest. It's a good point. I'll write it. For multi-class, one versus rest. Whenever you get a binary classifier, you can do this. So for example, you can say probability of cow versus not cow. Right. Then you can say probability of a horse versus not. Probability of a duck versus not. Not will mean, for example, in the case of duck, it is either a duck or it is horse or cow put together. Then you would compare these three probabilities, pick the highest. And find out which animal is it associated with. So that is why the logistic regression, when you apply to multi-class, you have to build, in a sense, three models or a number of classes. -1 typically.
So, Asif, I have a question. So the choice of decision boundary, I just want to clarify this, that is based on the cutoff probability of the given.
I can't hear you. You have to be a little bit louder.
So I just want to clarify the choice of the decision boundary. How do we choose the decision boundary that is based on the cutoff probability? Is that correct?
In other words, how do you find the decision boundary is your question, right?
Yes.
I do agree that we need to, once we find the decision boundary, this is the theory. The problem remains, how in the world do you discover that decision boundary itself? And that deals with our next topic, that is the loss function. How do you know that in the case of regression, you find the best fit line by using sum squared error loss function. So the next topic will be exactly that. How do you discover the decision boundary? How do you discover the decision boundary? And what is the loss function? It becomes the broader question, what is the loss function for classifiers. That itself is a bit of a mathematical digression, but today we have had enough. So I'll stop here and we'll talk about that next time because we are running out of time. It's 10:27. We have 3 minutes left. I would rather take questions because after that, I have my meeting with the India team. So, any questions, guys? By the way, was it clear? I know that we did a long intellectual journey today, but was it reasonably clear? Do you feel you understood it? Anyone?
Yes, sir.
Yes.
Good. So I'm going to
Yes.
yeah. I'm going to share this now.
Clear, sir.
Stopping the recording now. Oh, something strange happened. Maybe the recording of the second half didn't come through, or it did. I don't know what happened. It says record. So guys, the second half of the lecture may not have come through, in which case I will sort of repeat it at some point for you guys and re-record it, which is unfortunate. I'm just looking at it and it seems that I might not have gotten it. Let's hope that I got most of it. I don't know where I made a mistake and stopped it. But I'll post these notes and we'll take it from there. We have 2 minutes. If anybody has a question, please do ask.
Sir, I cannot play YouTube video still. I don't know. It says private.
Who am I talking about? Sukhpal, did you log in with your YouTube ID with the same Gmail ID? You have to log into YouTube, otherwise you can't.
Yes, sir. Yeah, I'm always logged in because I have YouTube Premium. So that only works when my email is
Reach out to
when
me
I'm logged in.
and or to Prachi. Prachi and Glennis, and could you guys please help him? I don't think.
Thank you, sir, and good night.
And do reach out to me, otherwise, if you can't reach Prachi and these people. I think Prachi is not here. And I don't see. I think Glennis was here. These people will help you. No? I'll help you. Any other questions, guys?
Message me.
All right, then. Good night. Good night.
I have a question. So the one with the transistors, the one where it either passes zero or it passes a signal, is that a sigmoid function or is that a different function?
It is a sigmoid.
It's sigmoid. I thought it was like the reducer.
Yeah.
It's not.
Yeah. No. Yeah. It is a. See, here's the thing. It is rectified. Doesn't go negative. Now, right from my electronics 30. But I remember that sigmoid
Hearing
function.
echo again.
I may be wrong. It is possible I'm wrong. So that's a good point to cross-validate. Go check it out in the textbooks. The current through a transistor is what is. In fact, we can check it right now. Transistor function of bias. I don't see the function here. Okay, I'll look at that. Huh? Maybe if I am wrong, I'll let you guys know. But from 30 years ago, if I remember right, it was the graph represents the current and voltage of a transistor. Current. Yes, it is like a sigmoid function, except that it doesn't have the current through it. The current. Okay, I'll look it up. Huh? I'll look up and I'll tell you. Maybe it is not exactly a sigmoid function. I used to always believe it is. Any electronics engineer here working with semiconductor physics?
Asif, I used to. Balaji.
So is it a sigmoid or is it not?
IV characteristics?
Yes.
It's actually, yeah, we don't, So after the threshold voltage, actually, threshold is not usually where we operate. There are sub-threshold operation region, but beyond threshold, we just look at the right side of the.
That is right.
Yeah, you're right. Actually, it's a sigmoid. Yeah.
It's a sigmoid. Good. Nice. All right, guys. Good night then.
Good night, Asif. Thank you.
Good night.
Good night.
Right away. Kate, let's get together sometime tomorrow afternoon for that, the government registration stuff.